Good morning, students. This is Latif sir. Today I am going to start the first chapter of class 12 chemistry. The topic is the solid state. In this chapter, we will study about what is solid, types of different types of solid, crystal lattice, unit cell, and calculation of number of particles and density of unit cell, and different types of defect in crystalline solid, and electrical and magnetic properties of solid. So let's start. First, you have to know what is solid. In lower classes, you have already studied that based on interparticle force of attraction and interparticle force of attraction and interparticle space, matter can exist in three different states. Based on interparticle force of attraction and interparticle space, matter can exist in three different states. One is solid, another is liquid, and the third one is gas. That is solid, liquid, and gas. And you know that the interparticle force of attraction is maximum in case of solid state, and interparticle space is minimum in solid state. That is, in solid state, the particles are very closely attached to each other. Okay, so first you have to know that types of solids. So see classification of solid. Solid can be classified in two classes, crystalline and amorphous. So solid can be classified as crystalline solids and amorphous solids. Okay. Wait. Solid can be classified in two forms, crystalline and amorphous form. Okay, this is on the basis of arrangement of constituent particles. Constituent particle may be atoms, ions, and molecules. Okay, so in crystalline solid, first see this picture. The first one is crystalline solid and the second one is amorphous solid. Okay, so crystalline solid, it is cleared from this picture. That is, in crystalline solid, the particles are very regularly arranged. Okay, but in amorphous solid, the particles are not regularly arranged. Okay, they are disorderly arranged in amorphous solid. So see, a crystalline solid is composed of one or more crystal. Each crystal has well defined ordered structure in three dimensions. A crystalline solid is composed of one or more crystal. Each crystal has a well defined ordered structure in three dimensions, and they have sharp melting point. Example of crystalline solid: sodium chloride, sucrose. Okay, these are some example of crystalline solid. Ice also is an example of crystalline solid. Now amorphous solids. I have told that in amorphous solid the particles are not regularly arranged or orderly arranged. They are disorderly arranged. Okay, so an amorphous solid has disordered structure. An amorphous solid has a disordered structure. It lacks with well-defined arrangement. It lacks with well-defined arrangement of basic units found in crystal. Okay, and they melt over a wide range of temperature. Example of crystalline solid: glass is an example of crystalline solid. Rubber, plastic, wood, these all are example of amorphous solid. Sorry. Okay, so so based on arrangement of constituent particles, that is, constituent particles means it may be atoms, ion, and molecules. Solids are two types, crystalline and amorphous. In crystalline solids, the particles are orderly arranged. Okay, in crystalline solid the particles are orderly arranged, very orderly arranged, and in amorphous solid the particles are disorderly arranged. Okay, so now see the differences between crystalline solids and amorphous solids. Crystalline solid, first, crystalline solid and amorphous solid. See the differences. In crystalline solid, these have definite and regular arrangement of constituent particles in space. Crystalline solid, they have definite and regular arrangement of constituent particles in space, while amorphous solid, this does not have. Amorphous solids, this does not have any regular arrangement of constituent particles in space. Second, crystalline solid, these are true solid. These are also called true solid because the particles in crystalline solid are regularly arranged, orderly arranged. Okay, but amorphous solid, amorphous solid, also called super cooled liquid or pseudo solid, because their particles are not regularly arranged or orderly arranged. Okay, that's why amorphous solids also called pseudo solids or supercooled liquid. Third point, crystalline solid, they have long ordered arrangement of constituent particle, very long range order of constituent arrangement of constituent particles. Okay, while amorphous solid, these have short order arrangement. Short amorphous solids, these have uh, short ordered arrangement of constituent particles. And fourth point, very important point, crystalline solids are anisotropic in nature. Crystalline solids are anisotropic in nature. Crystalline solids are anisotropics. Uh, See this term, anisotropic in nature, because this is because some physical properties like refractive index, electrical property are different in different direction in case of crystalline solid. That's why crystalline solids are also called anisotropic in nature. Anisotropic in nature because their physical properties, some physical properties like refractive index, electrical properties, these are different in different direction. While amorphous solids, these are isotropic in nature. Isotropic in nature. Isotropic means same, and isotropic means different. So isotropic in nature, amorphous solids are isotropic in nature. This is because their physical properties are same in all direction. Amorphous solids are isotropic in nature because their physical properties are same in all direction. And fifth difference, see fifth point, they have sharp melting point. Crystalline solid have sharp melting point. Amorphous solids melts over a certain range of temperature. Okay, amorphous solids melts over a certain range of temperature. Crystalline solid, they undergo a clean cleavage when cut, while amorphous solid, they undergo irregular cleavage when cut. Okay, so these are some basic differences between crystalline solid and amorphous solid. Okay, now see types of crystalline solid. Okay, so types of now see types of crystalline solid. In this chapter, we will study only about crystalline solid. Okay, so already we have already discussed about crystalline solid and amorphous solid, and now see types of crystalline solids. Based on the nature of bonding, crystalline solids are four types: molecular solid, covalent solid, metallic solid, and ionic solid. Crystalline solid, based on the nature of bonding present in the within the particle, crystalline solids are four types: molecular solids. In molecular solid, the force of attraction present is van der Waals force of attraction. In covalent solid, the force of attraction is covalent bond. In metallic solid, the force of attraction is metallic bond, and in ionic solid, it is ionic bond. Okay, so now see first type of crystalline solid is molecular solid. Okay, Molecular solid. This type of solids are made up of molecules. The particles are molecules generally. Okay, so a molecular solid is a solid that consists of atoms or molecules, generally molecules, held together by weak intermolecular force of attraction, that is van der Waals force of attraction. A molecular solid is a solid that consists of atoms or molecule held together by weak intermolecular forces. And this see some properties of molecular solid. uh, they are mainly soft, low melting point, they are volatile and electrically insulator. Okay, and poor thermal fusion. Now see example of molecular solid. There are many examples. Solid carbon dioxide is a molecular solid. Solid water, that is ice, is a molecular solid. Sugar, iodine, all these are molecular solid. In nonpolar molecules, the intermolecular force of attraction is mainly weak van der Waals force of attraction. Okay, but in case of polar molecular solid, the polar molecules have dipole, and so they have slightly stronger force of attraction between them, meaning that the melting point of polar molecular solid is a little higher, because more energy is needed to overcome the slightly stronger forces. Now second type of crystalline solid is metallic solid. Metallic bond is present in metallic solid. Hmm. So a metallic solid is a solid that consists of positively charged metal ion held together by a surrounding sea of electron. In metallic solid, metallic bonding is present, I have told. And in metallic solid, positively charged metal ions held together by a surrounding sea of electron. Okay, and this is this diagram, this picture. It is a this diagram showing that nature of particles. Okay, nature of bonding in metallic solid. And this spherical circle, these are metal ion, and each point represent electron. Each point in this entire diagram, each circle, each spherical ball is a metal cation, positively charged metal ion, and each point, you can see each point represents an electron. Okay, so see some properties of metallic solid. In this kind of solid, the bonding uh, kind of bonding, positively charged metal ion form the lattice, which is submerged in the sea of electron. In metallic solid, the metal atoms loses their valence electron and form a sea of electron. And within this sea of electron, the metal ions, positively charged metal ion, they floats on this sea of electron. And in metallic solid, the metals ions occupy fixed position in the lattice structure, and they are surrounded by delocalized electron. Therefore, the intermolecular forces in metal must be rather strong. And now see some properties of metallic solid. They are very soft to very hard, and they have low to high melting point. They are good conductor of electricity and heat. These are properties of metallic solid, and they exist as metallic luster. They are malleable, ductile, moderate heat of fusion. Okay, so example of metallic solid: any type of metals, iron, copper, silver. These are all are metallic solid. Now ionic solid, made up of ions, positively and negatively charged ions, that is cations and anion, like NaCl. Okay, so See, an ionic solid, an ionic solid is a solid that consists of cation and anion held together, that consists of cation and anions held together by electrostatic force of attraction between the among the positively charges, uh, opposite charges. Okay, that is, in ionic solids ionic bond is present. You can see this is the lattice structure of sodium chloride. Sodium chloride is the ionic solid. It is formed by Na plus and Cl minus. Okay, and I see some important properties of ionic solid. They are brittle, high melting point, and they are good conductor in aqueous solution. But in solid state, they are bad conductor. Or okay, so they are good conductor in aqueous solution or in fused state. Example of ionic solid salt like NaCl, KNO3, LiF, BSO4. All these are example of ionic solid. And this is this picture is a crystal lattice of ionic solid. Now covalent solid, last type of solid is covalent solid. A covalent solid, here in this type of solids covalent bonding is present. A covalent network solid is a solid that consists of atoms. It is formed by atom. So a covalent network solid is a solid that consists of atoms held together in large network or chain by covalent bond. Large network or by chain by covalent bond. Okay. And important properties of covalent solids: they are very hard. Example, first see the example of covalent solid: diamond, graphite, silicon carbide. These are example of covalent solid. And now see properties of covalent solid. They are very hard. Diamond is the hardest known substance, you know that. And they have very high melting point. They are poor conductor of heat and electricity. Exception is that graphite, although it is covalent solid, but it is a good conductor of electricity. So example of covalent solids: diamond, graphite, and silicon carbide. These are some example of covalent solid. Now see in this table four types of solids and their properties also given. Solids, types of solid: molecular solid. In case of molecular solid, melting point is low, and hardness and brittleness. Molecular solid soft and brittle. And molecular solid, they are non-conducting of electricity. Metallic solid, their melting point variable, and hardness and brittleness variable, hardness and malleable. These are metallic solid, and they are conductor of electricity. And okay, and ionic solid, they have high to very high melting point, um, and they are hard and brittle. And ionic solid are non-conducting in solid state but conducting in liquid state and in aqueous solution. And covalent solids, covalent network solid, they have very high melting point, and they are very hard, and they are usually non-conducting. Exception is graphite is a conducting covalent solid. Now see crystal lattice. What is crystal lattice? A crystal lattice is the geometrical arrangement of lattice point in a crystal. Lattice point means constituent particles which are generally represented by giving a point. Here you can see each point represent a lattice point. It is a particle. Each point represent particles. It may be ions, molecules, or atoms and molecules. And these points are called crystal lattice point. Okay, and this entire arrangement is the lattice, crystal lattice. This entire arrangement is a crystal lattice of crystalline solid. Okay, so and these small boxes are known as unit cell, which are repeated in okay. So these are two dimensional, these are actually two dimensional crystal lattice, and where this point represent lattice point. Okay, these are actually particles by which the crystalline solid is made up. These all are two dimensional crystal lattice. So what is crystal lattice? A crystal lattice is the geometrical arrangement of lattice point, that is particles, in crystal. Okay, so these are some two-dimensional crystal lattice. Two-dimensional, but in reality, the crystal or crystalline solids are three-dimensional, and their crystal lattice also three-dimensional. Three-dimensional. Actual crystal lattice means three-dimensional crystal lattice. Okay, for simplicity, it is showing two-dimensional crystal lattice. This entire is a crystal lattice, and each small boxes are known as unit cell, which are repeated. Okay, and different types of unit cell is shown here. Here you can see. Now see, unit cell. What is unit cell? I have told that these small boxes are known as unit cell. Unit cell is the smallest portion of a crystal lattice. This is the smallest portion. This is the entire is a crystal lattice, and the smallest portion of a crystal lattice is known as unit cell. Okay, so units, what is unit cell? A unit cell is the smallest portion of a crystal lattice that show the three-dimensional pattern of entire crystal. Three-dimensional pattern of the entire crystal. Okay, a crystal can be can be taught okay, so unit cell, first you have to know what is crystal lattice, and then unit cell. I have told unit cell is the smallest geometrical portion of a crystal lattice. Okay, and a crystal can be thought of as a same unit cell repeated over and over in three dimension. A crystal can be thought of as the same unit cell repeated over and over in three dimension. And different types of unit cell is shown here, and this is this figure, you can see this picture. This is a three-dimensional unit cell. Three-dimensional unit cell. This is a three-dimensional unit cell. You can see this is a three-dimensional crystal lattice. Sorry, this is a three-dimensional crystal lattice, and the smallest portion, this one, this is the three-dimensional unit cell. Okay, and it is shown here. You can see unit cell, and this entire is three-dimensional crystal lattice. Okay, this is three-dimensional, and the smallest portion of this smallest portion, which is repeated in three dimension, okay, which is known as unit cell. And here also it is shown unit cell. It look like a cube. Okay, and a unit cell is described by six parameter, three axis, and three angles alpha, beta, gamma between three interaxial angle, three in axis. Okay, so a unit cell three dimensionally a unit cell is described by three axes in three dimension, that is x, y, z, and the angle between this among these three axes, which are represented by alpha, beta, and gamma. Okay, so this is three-dimensional crystal lattice, and this is the actual crystal lattice, because actual crystal lattice is a three-dimensional, not two-dimensional. For simplicity, it is shown here two-dimensional crystal lattice. Okay, so a unit cell is the smallest repeating portion of a crystal lattice. If you repeat this smallest unit cell, you will get the entire crystal lattice. Okay, so a unit cell is the smallest repeating portion of a crystal lattice. And now see types of unit cell. There are different types of unit cell: a simple, cubic, face centered, cubic, body centered unit cell, okay, and end centered also. This type of unit cell, three-dimensional unit cell. First one is simple unit cell, second one is face centered unit cell, and third one is body centered unit cell. It look like this, okay. You can see there's a three-dimensional picture of defined unit cell: simple, face centered, and body centered. Now we have to know the definition of this type of unit cell, that is what is face centered, what is body centered, what is simple. So first type of unit cell is simple or primitive unit cell. Simple or primitive unit cell. Simple unit cell in which the particles are present at the corner of unit cell. In simple unit cell, you can see the particles are present at the corner of unit cell, okay. There are 8 corner and 8 particles are present at the 8 corner. If only 8 particles are present at the 8 corner of unit cell, then it is known as simple or primitive unit cell. Second one is face centered unit cell. Face centered, in case of face centered unit cell, there are 8 particles are present at 8 corner of the unit cell, okay. 8 particles at the 8 corner, and 8 as well as at the center of each of the 6 faces. Particles are present at the corners, at the 8 corners, as well as at the center of each 6 faces, okay. That is at the midpoint of each faces. One particles at the midpoint of each 6 faces, okay. You can see. So in face centered unit cell, in which particles are present at the corner as well as at the center of each of 6 faces. And now body centered unit cell. In body centered unit cell, the in which the particles, in body centered unit cell, the particles are present at the corner as well as at the center of the unit cell, at the body center of the unit cell. That is 8 particles at 8 corner or 8 vertex, and 1 particles at the body center of unit cell, 1 particle at the body center of unit cell, okay. So this is body centered unit cell. And last type of unit cell is end centered unit cell. End centered unit cell. In end centered unit cell, the particles are present at the corner, that is 8 particle at 8 corner, and at the center of 2 opposite faces, not at the center of all faces. At the center, 8 particles at 8 corners, and 2 particles at the center of 2 opposite faces, okay. So you can see 8 particles at 8 corner, and 2 particle at the midpoint of 2 opposite faces, okay. This type of unit cell is known as end centered unit cell. Now you have to calculate the number of particles per unit cell, okay. Just see this figure with this picture, okay. You have to remember that the particles present at this corner of a unit cell not is the not completely part of this unit cell only, okay. The particles present at the corner of a unit cell are shared between 8 such unit cell, 8 such unit cell. Each particle present at the corner of a unit cell, remember that, is shared between 8 such unit cell, okay. So for each particle present at the corner, the contribution to this unit cell is 1 by 8, because each particle only this is only 1 by 8 part is shared within this unit cell for each particle present at the corner, you have to remember. And the particle present at the midpoint of each faces, at the midpoint of each faces is shared between 2 such unit cell. The particle present at the midpoint of each faces is shared between 2 such unit cell. That is, this is the part of 2 unit cell. Okay, so the contribution of the each particle present at the center of each faces to this unit cell is half. Okay, and the particle present completely, that the particle present within the body center of the unit cell is completely part of this unit cell, so contribution is 1. Contribution to this unit cell is 1. Okay, so particle present at the corner of unit cell is shared between 8 unit cell, 8 such unit cell. So for each particle present at the corner of unit cell, the contribution to this unit cell is 1 by 8, and for each particle present at the midpoint of each faces, the contribution is 1 by 2, and the particle present at the midpoint of the unit cell is 1. Okay, so using this concept you have to calculate number of particles per unit cell. So total number of particles. So in case of simple cubic unit cell, I have told in case of simple cubic unit cell, there are 8 particles and 8 vertex, 8 corners, and for each particle the contribution to this unit cell is 1 by 8. So in the total number of particles in case of simple cubic unit cell is 8 into 1 by 8, that is on average one particle is present in simple cubic unit cell. Completely one particle is present within the simple cubic unit cell. Okay, in case of face centered unit cell, you know that in face centered unit cell particles are present at 8 corners, so contribution from corners is 8 into 1 by 8. And in face centered unit cell, there are 6 particles at the midpoint of 6 faces, and contribution for each face particle is 6 into half, 6 into 6 particle at the midpoint of 6 faces. So contribution for the particle present at the midpoint of each faces is 6 into half, that is 3. So total number of particles on average, total 4 particles are present in face centered unit cell. And in case of body centered unit cell, you know that in body centered also 8 particles at 8 vertex, so 8 corners, so contribution for each particle uh, 1 by 8 though. So total contribution for the corner particle is 8 into 1 by 8, and in body centered unit cell one particle is present at the midpoint of body center, so total contribution is 1. So total particle on an average, total 2 particles are present in body centered unit cell. In body centered unit cell, total on an average 2 particles completely present within the unit cell. And in case of end centered, in end centered unit cell, 8 particles at 8 vertex or 8 corners, so contribution for the 8 corner particles is 8 into 1 by 8, and 2 particles at the midpoint point of 2 opposite faces, so 2 into half, that is 1. So 1 plus 1, that is 2. On an average 2 particles are present in end centered unit cell. So again I'm repeating, in case of simple cubic unit cell, on an average 1 particles is completely present within the unit cell. In case of face centered unit cell, on an average 4 particles are completely present within the unit cell. In case of body centered unit cell, on an average 2 particles are present within the unit cell, and in case of end center, on an average 2 particles are present. Okay, so different types I have already told about different types of unit cell: face centered, body centered, simple, and end centered. And I have you have to remember this calculation number of particles per unit cell. Okay, and now types of crystal system. Types of crystal system. There are total 7 crystal system are found in nature. Okay, there are about 230 crystal form which have been grouped into 14 types of space lattice, also called Bravais lattice. On the basis of their symmetry, 7 different crystal system on the basis of interfacial angles and axes. I have already told, a unit cell, three-dimensionally a unit cell is represented, is described by three axes xyz, along xyz, and three angle alpha, beta, and gamma, three inter axis and three interaxial angles. Okay, so based on these values, uh, the edge length along three dimension, that is ABC, which is A, B, and C, and the angle between three axes is alpha, beta, gamma, and based on the relation between these ABC and alpha, beta, gamma, unit cell, uh, crystal system are seven type. There are seven crystal system. See, you have to remember this relation for crystal system. The relation between edge length ABC is A is equal to B is equal to C, and the relation between the angles alpha, beta, gamma is 90 degree. For tetragonal, the relation between A, B, C is A is equal to B, not equal to C, but relation between alpha, beta, gamma is angles are alpha is equal to beta is equal to gamma is equal to 90 degree. For orthorhombic crystal system, the relation between A, B, C, edge length along three dimension, three direction, three axis, is A is not is equal to B not is equal to C, but the angle alpha is equal to beta is equal to gamma is equal to 90 degree. For hexagonal, for hexagonal crystal system, you can see this is hexagonal crystal system, and in case of hexagonal, A is equal to B not is equal to C, but alpha is equal to beta is equal to 90 degree, but gamma is 120 degree. Okay, you have to remember this relation relation between ABC, that is three edge length along three dimension, three direction, three axis. Okay, and alpha, beta, gamma, three and interaxial angles, and rhombohedral crystal system, where A is equal to B is equal to C, but alpha is equal to beta is equal to gamma not equal to 90 degree. Monoclinic, A is equal to B not is equal to C, but alpha is equal to beta is equal alpha and gamma is equal to 90 degree, and beta not is equal to 90 degree for monoclinic. And for triclinic, A not is equal to B not is equal to C, and alpha not is equal to beta not is equal to gamma not is equal to 90 degree. So most symmetrical crystal system is cubic crystal system. And in this chapter, you have to I will discuss only about cubic crystal system. Okay, and most unsymmetrical crystal system is triclinic crystal system. Okay, so you have to remember these seven different type of crystal system based on the values of ABC, that is edge length along three different axes, edge length of unit cell, and three interaxial angle, that is alpha, beta, gamma, between these three interaxis, between these three axes. Okay, so in next video I'll discuss about packing efficiency, packing fraction of crystal system, different crystal system. Bye students.